Okay, to start Bernoullis principle, I want to use the formula or talk about getting this formula right here. So, I'll bring this down a little bit. Well, I thought I was going to talk about how to get that formula, but I can't seem to pull this down. I think I'll just, instead of trying to pull that down, wait a second, there we go. Oh, I did it. All right. So, conservation of mass talks about the fact that we're not going to lose any mass in going from one pipe to another. What we're going to basically do here is take the mass, which is going to be the density times the volume. Remember, the density is just grams over, say, some sort of volume, say liters. So for that, I multiply it by the volume, and liters, I just have the mass. So we can say that the mass is equal to density times the volume. We're going to substitute that in, and then we talk about a lot of pipes and cylinders. So if we do that, the area is going to be here times the length. Substitute that in, and what we are going to end up with is the cross-sectional area that we talk about here times the velocity of the fluid through it is going to be conserved. Now let's say that we have another pipe that we're laying here, and all we're saying is that the velocity of the water that's going through here is going to go through at a much faster rate because the surface area, cross-sectional area, is so much smaller. So what we come up with, because of the conservation of mass, is that the cross-sectional area, pi r squared, times the velocity is going to equal pi r squared of the second times its velocity, the final velocity. That's going to be conserved. And this is really no different than you taking a hose in the summertime and putting your thumb over it and decreasing the area, and the water shoots out a whole lot faster. So if we were to look at this example here, water flowing through a 20 centimeter squared cross-sectional area at a rate of 6 meters per second, entering a smaller pipe at 5 centimeters squared, how fast would it be moving? Well, we're going down by a fourth, and that's going to basically mean that it's going to go up by a fourth. So A1 V1 equals A2 V2. We're going to have 20 centimeters squared going at 6 meters per second. We're going to go to 5 meters per second. Sorry, 5 centimeters squared. What we'll find here is that the velocity is 24 meters per second, 4 times the velocity, because we have decreased by 4. All right, Bernoulli's principle comes from a conservation of energy, and this is going to look really familiar to you. 1/2 mv squared plus mgh. That's the energy we looked at quite a bit anyway. There were other types of energy, but we looked at those types, kinetic and potential, gravitational potential. But what we're going to talk about here is that there's work being done to change a pressure, for instance, compress. And so pressure volume work is something that's going to be have to be considered for energy, because that is work that's being done. So we're going to do a little bit of substitutions here. If we account that density is mass over volume, and conversely, density times volume is going to be mass, we will substitute that in for m, divide through by volume, and what you end up with, if you look at the units closely, is 1/2 rho v squared, and then rho being density, plus rho gh, plus the pressure in pascals. And that's going to be constant. It's going to be conserved, just like it was before. So this should look at least a little bit familiar to you, except that now what we're doing is we're looking at the before and after situations where this is rho density and this is pressure pascals. So it's going to be 1/2 rho v squared. That's, by the way, the initial velocity squared, just as the superscripts and subscripts don't come across real well here. And this is rho gh, 1, meaning rho g height 1. This is the pressure in pascals of the before. So what I mean by 4 is maybe a pipe with a little bit wider surface area and one that has a narrow. So we're having water flow through this, and now the water is going to flow through this. So this would be the before, and this would be the after. And so afterwards, we have 1/2 rho v sub 2, or the second velocity squared, plus rho gh2, the second height, plus the pressure in this tube right here. Okay. So again, just like we did with the other concept, what we can often find is that variables can be eliminated. For instance, if there is no height elevation, we can get rid of rho gh. Just like when we had a ball coming down, or something sliding down a hill, we had height to start, but at the bottom we had no height, we had all velocity. Up here we just had velocity, here we just had, up here we had height, and down here we had velocity. So here what we're going to do is we could eliminate height. There's some other things we can do. You may mention them here, but quite honestly, when we get to them, I'll talk about how these can be eliminated. The biggest thing with Bernoullis is that we see that in a fluid whose density doesn't change, the pressure and the velocity are inversely proportional. Faster moving fluids have less pressure in them. Let's give you some. Definitely try this. Take 2 pieces, actually do this one right here. Hold 2 pieces of paper, okay, and about 1 inch apart, blow between them, and you see they come together. If you've ever been in a shower with a shower curtain, and the water's coming down and the curtain seems to be coming in at you, all that's happening is you're creating a low pressure system in the shower, and the atmospheric pressure on the outside of the curtain is pushing it in on you. We never really use this term sucked, because nothing sucks in physics, it just lacks air pressure. So try this. If you take a stream of water, turn the water on really high, and then just very lightly hold a plastic spoon at the very top, kind of letting it dangle almost. Bring it closer to the water, and you'll see that there's just a push of the atmospheric pressure pushing that spoon into the falling water. Cars passing each other on a highway, this is kind of important for you to take some notes on, because there's a little essay question. So let's say that there's a big semi-truck and you're going, this way on the highway. Well, the airflow coming at you, what's going to happen here is this narrowed area, this is a narrowed area, meaning that our cross-sectional area is gone down, which means our velocity is going to go up. So we have a high velocity area between the two cars. Now, that's the first thing you want to mention. The second thing you want to mention is that if you have an increase in velocity, you have a low pressure system. So what's going to happen? Third thing you should mention is that the atmospheric pressure from the outside, this just regular atmospheric pressure, is going to push the two things together, the semi-truck and the car. So first of all, talk about the fact that the area between the two vehicles is narrowed, and a cross-sectional area that's lower leads to a high-speed fluid flow, velocity. A high-speed fluid flow leads to a low-pressure system. And thirdly, the atmospheric pressure on the outside pushes the two things in. Oh boy, I can't write with this. That's supposed to be outside. Atmospheric pressure on the outside pushes vehicles together. That is really bad handwriting. But hopefully you get the idea. So that's going to be an essay question. Make sure you understand. Okay, a couple other things for Bernoulli's principle. We have an airplane wing, and this is pretty simplistic, but just in general, got this glob of air, which is actually a technical term, believe it or not. And this air is going to go over the wing. Now the way that this is designed, this air, this part of the glob, has to go farther and therefore faster. If you use that little 3 dot symbol, means therefore. This air goes farther, therefore it must go faster. Well, you know the story. If it goes faster, the velocity of the air is going faster. There's a low pressure system there. Over here, this is just a regular high pressure system, or higher pressure anyway. So if I've got a higher pressure down here and a lower pressure there, we're going to get an overall lift of the airplane wing. Smoke coming out of a chimney. What you're going to have up here, higher elevations generally mean faster winds. If you build a fire and it's very still outside, there isn't a lot of winds, that's not generally when you are building a fire. So you're okay normally building a fire because you're going to have a windy, turbulent, cold day, and you will have faster winds. So higher elevations, usually you're going to get faster winds. If you get faster winds, of course, again, low pressure system. Well, inside the house, you just have regular atmospheric pressure. So what's going to happen to the smoke that's inside the house? Well, the smoke inside the house is going to get pushed up toward the low pressure system. So the regular atmospheric pressure in the house is going to push that smoke up and out toward the lower pressure system that's happening outside. So if you have a very still day, sometimes you'll get the smoke in the house. You don't have enough of the pressure differential to push that smoke out of the house. Okay, prairie dogs. This is a prairie, so very windy. But prairie dogs will build different holes at different elevations. Why? Okay, again, high elevations, faster winds, low pressure system. Lower elevations, a little bit slower winds, and just have a regular, a little bit higher pressure. So what's going to happen here from a higher pressure, this air is going to, from the higher pressure, get pushed up toward the lower pressure. And the prairie dogs have an airflow. And these are on the prairies. This is a very windy area, unlike some places. And lastly, dangers of a tornado. If you have a tornado that's going on outside, that's why tornado, you are having a very high speed wind, right? The velocity is very fast. You're creating quite a low pressure system. Now, if inside the house, the house is all boarded up and you just have regular atmospheric pressure, what ends up happening is you can actually get the windows or the doors or even the roof blown out. But what's really happening is the air inside is pushing them out against an extremely low pressure system. I've also heard of stories of people going out once the tornado sirens go off. They go outside to see what's happening, not recommended, but they go outside to see what's happening. Well, then they see that, a tornado really is coming, so then they try to get back into the house. Now, why can't they get back into the house? Well, because this pressure is so high inside compared to outside that they can't push against that door with enough force to get back inside the house.